Hello, my name is Chen, and my team member Jack Carr and I will be discussing the I-35W Mississippi River Bridge collapse in 2007 due to fatigue failure in its structure. The I-35W Mississippi River Bridge, also known as Bridge 9340, was an 8-lane steel truss bridge that collapsed due to fatigue failure that was observed in a critical part of its truss structure. Construction on this bridge originally began in 1964 and at first was completed and opened to the public 3 years later in 1967. During rush hour on August 1st, 2007, the bridge catastrophically failed. At the time that it failed, it was the third busiest bridge in Minneapolis, with over 140,000 vehicles passing over it daily. At 6:05 p.m. on August 1st, 2007, the central portion of the bridge gave away and led to the subsequent collapse of all other sections of the bridge. As a result, 13 people died and about 145 people were injured. Over 111 civilian vehicles and bridge servicing vehicles were affected by this collapse. Following the incident, Minneapolis had to apply for $65 million in emergency federal aid, and rebuilding the bridge cost them $234 million, eventually totaling over $400 million when accounting for lost revenue due to the accident.
Following the collapse of the bridge, Minnesota's governor ordered the inspection of that bridge as well as all similar bridges composed of trusses. A corrosion engineer named William Schutt tested the bridges for de-icing salt, which in a high concentration causes corrosion in the steel of that bridge. Mr. Bazant learned by watching recordings of the bridge. By watching those recordings, he could see that the collapse started near the supports, possibly from gusset failure. In addition, the National Transport Safety Board investigated the bridge design. So they looked at the bridge in concordance with what it's supposed to be designed as to look for any possible miscalculations or wrongfully placed materials or something like that.
A major design flaw was what led to the ultimate failure of the bridge. Gusset plates that held the center beams of the bridge together were only half an inch thick when they should have been twice this at a full inch in thickness. Moreover, at the time the bridge failed, it was rated to be in poor condition by inspectors for over 17 years, and out of 120 points, it only scored a 50 on its structural integrity evaluation. Poor maintenance and ultimately neglect by the Minneapolis Department of Transportation is to blame for this accident. While signs of cracks were not clearly visible in the bridge, this failure could have been prevented with stronger repair efforts by the state. At the section of the first failure of the bridge, which was Bridge Pier number 6, investigators identified fatigue failure in all 4 of the gussets that were located there. The fatigue failure of these gussets set off other sections of the truss to fail in sequence due to overloading. At the time of the failure, bridge servicing vehicles and equipment totaling to about 300 tons were also reported to be stockpiled on the bridge. This additional loading definitely caused the acceleration of the fatigue cracking that were on the affected gussets.
The solution to the bridge's collapse was a multifaceted one. They begun with designing a new bridge that was built with high-strength concrete and lots of sensors that measure the bridge's conditions in real time to monitor it closely. Minnesota also inspected the gusset plates in every truss bridge to ensure that current bridges were not going to undergo the same failure. A $2.5 billion bridge improvement program was implemented that was set to replace or repair all deficient bridges within 10 years of the collapse. Drones were used to easily inspect hard to access parts of the bridge where typically inspectors couldn't get to. The state of Minnesota ended up repairing or replacing over 138 bridges, and they also identified all the bridges that would require routine maintenance so that they could keep a closer eye on them with new standards. The solution brought forth by the state of Minnesota was all around an effective one. By inspecting all of the truss bridges in Minnesota, each bridge that was deemed deficient was given a timeline to be brought back to repaired or established a maintenance schedule to keep them functioning properly. Once the state was conscious of the design flaw in the bridge that caused the failure, they could fix it for the rest of the bridges and keep them secure. This was done through the $2.5 billion campaign, and that campaign was successful in rehabilitating or replacing 138 bridges. So it was all around an effective solution. One particular aspect of the bridge that plagued it was its susceptibility to vibration. Thousands of cars pass over it all the time, sending little vibrations that weaken the supports and lead to cracks and failures. A proposed design improvement would be through a material called suborethane. It's a polymer, and its role is to reduce impact forces. There are statistics that say it can reduce impact force up to 80%. At frequencies from 10 to 30,000 hertz. It is weather resistant, so it would last on the bridge. But its importance is that by reducing those impact forces, it will reduce the vibration and force on the joints and supports of the bridges. So less vibration equals less wear and less fatigue, allowing the bridge to last much longer without cracks. A potential downside of the polymer would be it does not have the strength or resistance to load like steel would or concrete. But if the polymer was placed parallel to the bridge, it would not be taking on any kind of shear components. It would only be under compression, which would lend all the benefits of the vibration reduction without any of the of the penalties of its non-strength.